All right, here's a classic detour proof problem. Let's first of all we're going to need save some space. So I'm going to write given. You can see that in the picture, and I'll even write it up here. It says AC, those are equal to each other. It says these are equal to each other, and it says these are equal to each other. So the second step that we want to say is that angle ABE is congruent to angle ACE. Those two angles are congruent, and the reason is because a lot of times books will let you just do this. If sides, then angles. In an isosceles triangle, if sides, then angles. Step 3, so that means that that is equal to that. Let me draw that on the inside. That angle is equal to that angle, right there. Step 3, we're going to use the division property to prove that angle DBE is congruent to angle DCE. This angle right here is actually congruent to this angle right here. And that's called in most books call it the division property or division of congruent angles. Division property. I'll call it the division property. It's the division of congruent angles produces congruent angles. If I bisect an angle that's congruent to another angle, then those two smaller angles are equal. So that's really what I have here, which really means all 4 of those angles are equal to each other. I don't really need that. I just use the division property to show that those are equal. Now the next step I'm going to use, step 4, says since those angles are equal, I know that BD, the segment BD, is congruent to the segment CD. And that's kind of like number 2, the red one that we just did, but it's the opposite direction. If angles, then sides. On an isosceles triangle, if angles, then sides. So I know that that is equal to that right there. Now, step 5 is I'm going to show that the two triangles, triangle A, B, well, I should have done one more thing first. I should have said that for number 3, I'm going to go back and write it in. I know I said it, I didn't write it though. I'm also going to say that angle ABD is congruent to angle, basically all of those angles are congruent to each other, is congruent to ACD. So really all 4 of those angles are congruent to each other, like I mentioned, because I'm going to want to use that in this next step. I want to say that ABD, triangle ABD, is congruent to triangle ACD. And that's because now I have, you can see I have a side, angle, side. Okay, so if I have that, now I'm going to say, the next thing I'm going to say is that angle BAD up here, I'll put a little circle on that, is congruent to angle EAC. And that's because CPCTC, corresponding parts of congruent triangles, are congruent. So I know that those are equal to each other. That was a big detour. But now that I know that, I'm going to mention one more part of my detour here. I'm going to mention that this EA right here is equal to itself. 7 AE equals AE. And of course, that's the famous reflexive property. And then, almost done, not quite, but almost. Number 8, now I can finally say that triangle ABE is congruent to triangle ACE. Notice I said triangle, not angle. And the reason for that is Now I have side, angle, side. Side, angle, side. And since that's true, still not done, I'm going to do a double line over here. So here's number 9. Now I can say BE is congruent to EC, and the reason for that is CPCTC. And finally, number 10, I'm going to say that AE bisects BC. AE bisects BC, and that's just the definition of bisect. Or if congruent, then bisect, however you want to write it. I'm just going to write definition of bisect, because usually that's good. There it is. That's a long detour proof. Now, could there have been a shorter way to get to that? Maybe. And if you know the shorter way, go ahead and show me on the comments below.